Welcome to our breakdown of metal finishing. Today we are looking at sections 6.1 through 6.4 of the manufacturing manual, covering the core principles of electroplating, followed by the specific mechanics of chrome, zinc, and nickel. Selecting the right material requires understanding how the underlying electrical mechanism actually works. This diagram represents the starting point of an electrolytic cell. Electroplating is a process that uses an electric current to reduce dissolved metal cations, so they form a coherent metal coating on an electrode. The most common point of confusion is terminal placement. The setup rule is straightforward. The negative terminal of your power supply always connects to the target object you intend to plate. The positive terminal connects to the pure metal that will provide the coating. In this example, we are using a block of pure silver. When power is applied, the pure silver dissolves into the silver nitrate electrolyte solution, migrates across the bath, and deposits firmly onto the negative terminal, leaving behind any impurities. This basic circuit setup remains identical in almost every application. The mechanical properties of your final product are dictated entirely by the specific metal you choose to attach to that positive terminal. Looking at these plumbing fixtures, we see the most common baseline application of chrome plating. This thin layer of chromium provides a highly reflective, scratch-resistant surface that protects the underlying object from basic daily wear and corrosion. When we examine industrial machinery, we use a thicker application known as hard chrome plating. The extremely low friction of this chromed layer significantly reduces operating temperatures inside moving parts like rotors and pistons. This superior smoothness allows equipment to process highly abrasive materials like paper, limestone, or sand without compromising the lifespan of the interior components. This cross-section illustrates zinc plating, which solves a completely different engineering problem through a counterintuitive method known as a sacrificial coating. Here, we see a steel pipe coated with zinc, exposed to water and oxygen. Instead of acting as an impenetrable shield, the zinc intentionally attracts the corrosion. It oxidizes into a matte zinc oxide, essentially destroying itself to ensure the steel substrate beneath remains perfectly intact and isolated from the rust. Because this process is highly effective and inexpensive, manufacturing relies on zinc electroplating for heavy-duty structural components exposed to the elements. Everything from automotive brake calipers and power steering lines to military tanks and armored personnel carriers. Chrome protects a machine's moving parts by refusing to yield to friction, while zinc protects structural integrity by intentionally absorbing the environmental damage. Section 6.4 brings us to nickel plating. Nickel offers excellent ductility and hardness, but its defining characteristic is high solderability. This makes it the industry standard for electronic components like microprocessors, integrated circuits, and delicate electrical contacts. Beyond electronics, nickel possesses a secondary property that makes it vital to general manufacturing: exceptional adhesion. When a base metal is too rough for a final decorative finish, it is first plated with an undercoat of nickel. This fills the microscopic imperfections and creates a perfectly bonded surface for a top-tier layer like chromium to lock onto securely. Let's test your understanding of the initial circuit setup. If you are preparing an aluminum casing to receive this nickel undercoat, which terminal of your power supply must the aluminum connect to? It must connect to the negative terminal. The object receiving the deposit always acts as the negative electrode. This matrix synthesizes the material properties we've covered. You select zinc for cost-effective sacrificial protection against rust. You use chrome when you need extreme surface hardness and reduced friction. And you rely on nickel for highly solderable electronics or as a crucial bonding undercoat. The electrical principles driving the cations across the electrolyte bath are identical in every case. Engineering success requires matching the specific chemical behavior of your plating metal to the exact environmental threats your product will face. Here are two freshly machined aluminum blocks. On their own, they look identical, but we have to protect them from totally different failure modes. Pick the wrong surface finish, and you guarantee problems down the line. You will see accelerated corrosion, rapid mechanical wear, or dimensional shifts that completely throw the whole part out of tolerance. By the end of this, you'll have the exact criteria to specify the right coating for both your final parts and the specialized tools used to machine them. We will evaluate this in 2 stages. First, we'll evaluate the primary finishes for parts, powder coating and then anodizing. Then we will look at the tooling itself, specifically PVD and CVD vapor deposition coatings, before breaking down how these choices interact with raw materials. Starting with powder coating, this is a moderately priced method for adding a highly durable, wear and corrosion-resistant functional layer that is compatible with almost all metal types. But it has a severe structural limitation. Because it relies on an electrostatic application process, the charged powder particles struggle to penetrate deep cavities. You cannot effectively coat the internal surfaces of a component. It also applies thickly, which offers far less dimensional control than other methods. If you are working with small microcomponents, powder coating will instantly throw them out of spec. And aesthetically, any deep tool marks left from the initial machining process will often cure right through the powder and remain visible. Powder coating acts as a robust brute force exterior shield, but it lacks the precision required for tight tolerance internal engineering work. For precision on aluminum parts, you turn to anodizing. This process electrochemically grows a honeycomb-like, non-conductive ceramic structure directly out of the raw aluminum substrate. Standard anodizing is ideal for aesthetic integration. Because this ceramic layer is porous, it can be dyed to produce a smooth, rich surface color. This leaves a clean, highly aesthetic finish suitable for highly visible consumer or industrial components. When physical stresses increase, we move up to hard coat anodizing. This is a premium cost, high-density alternative engineered specifically for severe functional applications. Hard coat typically builds a 50 micrometer thick, undyed layer that provides absolute maximum corrosion and wear resistance. The engineering advantage here is exact control. For both types of anodizing, critical tight tolerance areas can be physically masked off to prevent any coating buildup in the chemical bath. Anodizing offers the exact dimensional control and chemical integration that powder coating lacks, making it mandatory for high-precision aluminum parts. Now that we've protected the final parts, we have to protect the specialized tools required to cut them. Tool coatings rely heavily on physical vapor deposition, or PVD. Operating between 400 and 600 degrees Celsius, this process evaporates metal and reacts it with nitrogen to form nanometer-thin lamellar layers. You compare this against chemical vapor deposition, or CVD. CVD operates at higher temperatures to create much thicker coatings, giving tools heavy crater wear resistance for general turning and boring of steel. The baseline PVD coating is titanium nitride, or TIN. Easily identified by its gold color, TIN adds a self-lubricating property that performs perfectly on alloy steel and plastics. For abrasive materials, you upgrade to titanium carbon nitride, or TiCN. It has a blue-gray color, increased hardness over TIN, and is engineered specifically for tough materials like ductile cast iron. For extreme environments, you select aluminum titanium nitride, or AlTN. This coating delivers superior oxidation resistance, built to survive high-heat, high-speed applications. This chart shows exactly how engineers map these specific chemical coatings to standardized insert geometries, perfectly matching cutting-edge shapes and relief angles to the operation at hand. Selecting the correct vapor deposition coating dictates your feed speeds, thermal limits, and overall factory production efficiency. Let's review the methods side by side. Anodizing delivers exact dimensional masking and aesthetics for aluminum, while powder coating provides heavy impact resistance across all metal types. During manufacturing, specialized tool coatings actively alter the raw material's behavior. The right coating prevents built-up edges and stops smearing during high-speed stainless steel milling. Specific cermet or PVD grades act to keep cutting forces exceptionally low. That low friction is exactly what enables the close tolerances and shiny surfaces required in a final finishing pass. Your surface finishes act as active mechanical variables that dictate both how the part is manufactured and whether it survives in the field. You now possess the exact technical criteria required to finalize your manufacturing specification sheets without risking a dimensional failure. For parts, powder coating provides broad exterior durability, Standard anodizing offers aesthetic ceramic integration, and Hardcoat delivers a functional 50 micrometer shield. For tools, rely on TIN for general lubrication, step up to TICN for tough cast irons, and deploy ALTN for extreme high heat operations. Review your current part blueprints and update your finish callouts based on these distinct tolerance and material rules. A part is only as good as its surface. Specifying the right coating is your final line of defense in modern engineering.
Let's study more, and like, share, and subscribe for such more content. And comment something you want to learn.